The pilot's name has been lost. What survives is the report, filed by his wingman, who watched it happen from 300 yards off the right wing. They were flying B-26 Marauders out of a base in England, summer of 1943, on a low-level mission against a rail yard in occupied France. The B-26 was powered by two Pratt Whitney R-2800 double Wasp engines, the same engines that powered the Thunderbolt, the Hellcat, the Corsair, the most reliable radial engine in the American arsenal, the engine that crews trusted with their lives because it had earned that trust mission after mission in conditions that would have killed anything less. The wingman saw the left engine trail a thin ribbon of white smoke, then a thicker stream of gray, then nothing at all. The propeller stopped turning. The B-26 yawed left, the dead engine pulling the aircraft toward the ground like an anchor dragging a boat into the current. On a twin-engine bomber flying at 200 feet above the French countryside, losing an engine was not an emergency. It was a death sentence. There was no altitude to trade for airspeed. There was no time to feather the propeller and retrim the aircraft. There was only the physics of asymmetric thrust, the living engine on the right wing pushing the airplane into a roll that the pilot could not correct before the left wing struck a row of poplar trees at the edge of a farmer's field. The aircraft cartwheeled. There were no survivors. The R-2800 had not failed because it was a bad engine. It had failed because a piece of shrapnel from a light flak gun had severed an oil line. Without oil, the engine seized in less than a minute. No engine can survive without lubrication, no matter how well designed, no matter how meticulously manufactured, no matter how many hours of testing it has passed on a factory bench in East Hartford, Connecticut, where the air is clean and no one is shooting at you. This is the truth about the Pratt Whitney R-2800 that the legend does not include. The R-2800 was the best radial engine of the Second World War. It was the most reliable, the most powerful for its size, the most forgiving of abuse, the most resistant to battle damage. It earned every word of praise that has been written about it in the 80 years since it first turned a propeller. But it was still a machine, and machines, when put inside weapons that are flown into combat, exist in a world where reliability is a prayer, not a guarantee. The story of the R-2800 is not a simple story of engineering triumph. It is a story about what happens when a brilliant machine meets a world that is determined to destroy it. The double Wasp began in 1936 in a factory in East Hartford, Connecticut, where a company called Pratt & Whitney had been building the engines that America flew on for a decade and a half. The company's founder, Frederick Rentschler, was a man who had staked his entire career on a single conviction, that air-cooled radial engines were superior to liquid-cooled inline engines. Air-cooled engines had no radiators to puncture, no coolant lines to leak, no water pumps to fail. They were lighter, simpler, and, Rentschler believed, tougher. A liquid-cooled engine that took a bullet through its radiator was dead within minutes, its coolant draining away, its temperature climbing until the metal seized. An air-cooled engine that took a bullet through a cylinder might lose that cylinder's power but keep running on the remaining 17. This was not theory. It was Pratt & Whitney's founding religion, and it had been proved correct in engine after engine, from the original 9-cylinder Wasp of 1925, the engine that had made the company's reputation, through the twin Wasp and the Hornet and every variant that had followed. By the mid-1930s, Pratt & Whitney engines powered more American military aircraft than all other manufacturers combined. The U.S. Navy, in particular, was a devoted customer. A naval officer, whose name has been lost to the informal history of engineering arguments, once dismissed liquid-cooled engines with a phrase that became legendary inside Pratt & Whitney's walls. A water-cooled aircraft engine, he said, makes about as much sense as an air-cooled submarine. The R-2800 was conceived as the next step in Pratt & Whitney's radial engine dynasty. The company already had the R-1830 Twin Wasp, a 14-cylinder engine that was the most widely produced American aircraft engine of the war. But the R-1830's growth potential was limited. Pratt & Whitney needed something bigger, something with more cylinders, more displacement, more power. something that could keep pace with the fighters and bombers that were being designed on drawing boards in 1936, aircraft that would need 2,000 horsepower or more. The answer was 18 cylinders arranged in 2 rows of 9, displacing 2,804 cubic inches, 46 liters. Each cylinder had a bore of 5.75 inches and a stroke of 6 inches. Each piston displaced roughly as much volume as an entire modern Subaru engine. The complete power section, with its crankshaft, connecting rods, pistons, cylinders, and valve train, was a masterpiece of mechanical packaging. 18 cylinders arranged in a circle barely 42 inches in diameter, producing 2,000 horsepower from a package that weighed 2,200 pounds. The first R-2800 ran on the test bench in 1937. It ran, but it did not run well. The early R-2800 had cooling problems. This was not a surprise. It was an inevitability. An 18-cylinder radial engine generates enormous amounts of heat. In a 2-row radial, the front row of 9 cylinders receives the direct blast of cooling air from the propeller. The rear row receives whatever air makes it through the gaps between the front cylinders, air that has already been heated by passing over the front row's fins. The rear cylinders run hotter. They always run hotter. This is physics, and it cannot be negotiated with. In the R-2800, the problem was compounded by the engine's relatively small displacement per cylinder. Each cylinder displaced roughly 156 cubic inches, less than competing designs like the Wright R-3350, whose cylinders displaced 186 cubic inches. Smaller cylinders mean more heat generated per unit of surface area because the power output scales with displacement while the cooling surface area does not scale at the same rate. The R-2800 cylinders ran hot because they were working harder relative to their size than the cylinders of any previous Pratt Whitney engine. The solution was engineering, not reinvention. Pratt Whitney's metallurgists developed advanced cooling fins, thinner, more numerous, more precisely formed than any previous radial engine, that increased the surface area available for heat dissipation. The fin design was so advanced that it became one of the R-2800's distinguishing features. Where earlier engines had thick, widely spaced fins that looked like the teeth of a coarse comb, the R-2800's fins were thin, closely packed, and machined to a uniformity that allowed air to flow between them with minimal turbulence. The effect was transformative. The rear cylinders still ran hotter than the front, but the differential was manageable. The engine could sustain full power without overheating as long as it was properly cowled and properly operated. The cowling was critical. An air-cooled engine lives or dies by its cowling, the shaped metal shroud that surrounds the engine and directs the cooling airflow. Too tight and the air cannot circulate. Too loose and the aerodynamic drag is unacceptable. The cowling designers at Pratt & Whitney and the airframe manufacturers who integrated the R-2800 into their aircraft, Vought, Grumman, Republic, Martin, Douglas, Northrop, spent thousands of hours in wind tunnels and on test flights refining the cowling shapes. The result was a series of installations that balanced cooling and aerodynamic efficiency with a precision that previous generations of engine designers had not achieved. The F4U Corsair's prototype, the XF4U-1, flew with the R-2800 on May 29, 1940. In October, during testing at the Anastasia Naval Air Station, the Corsair became the first single-engine American fighter to exceed 400 miles per hour in level flight. The engine had arrived. But the engine's first combat reputation was not earned in a fighter. It was earned in a bomber, and the reputation was, for a time, terrible. The Martin B-26 Marauder was a twin-engine medium bomber designed around the R-2800. It was fast, sleek, heavily armed, and extraordinarily difficult to fly. The B-26 had small wings for its weight, a wing loading that was, when the aircraft was fully loaded, among the highest of any bomber in service. This made it fast in level flight, but it also made it unforgiving at low speeds. The stall speed was high. The landing speed was high. The margin between controlled flight and an uncontrolled departure from controlled flight was thin enough that even experienced pilots found it alarming. In training, the B-26 killed crews at a rate that earned it a series of grim nicknames: the Widowmaker, the Flying Coffin, the Baltimore Whore, because, like the women of that city's red light district, it had no visible means of support. The joke was dark because the reality was dark. At MacDill Field in Florida, where B-26 crews were trained, the accident rate was high enough that an investigation was launched. The issue was not the engine. The R-2800s and the B-26 were the same reliable, powerful units that would later prove themselves in every fighter and bomber in the American arsenal. The issue was the airframe, the combination of high wing loading, high landing speed, and the asymmetric thrust characteristics of a twin-engine aircraft that was intolerant of pilot error. A B-26 that lost an engine on takeoff was in serious trouble. The aircraft was heavy, the wing was small. The remaining engine, even at full power, might not produce enough thrust to overcome the drag of the dead propeller and the asymmetric yaw. At low altitude, the pilot had seconds to identify the failure, feather the dead propeller, apply full power to the remaining engine, and maintain directional control while the aircraft wallowed at the edge of a stall. Experienced pilots managed it. Inexperienced pilots, fresh from training on lighter, more forgiving aircraft, sometimes did not. The R-2800 bore the blame unfairly. The engine did not fail. The engine was, in fact, performing exactly as advertised. But because the aircraft was difficult to fly on one engine, any engine failure, however rare, became a potential fatality. The Marauder's reputation as a killer was, in truth, a reputation earned by the airframe, not the engine. But reputations do not observe distinctions. The men who flew the B-26 remembered the fear, and the fear attached itself to everything about the aircraft, including the engines. When the B-26 was finally used in combat, in the Mediterranean and then in Northern Europe, at medium altitude rather than the suicidal low-level attacks that had characterized its early missions, it proved to be one of the most effective bombers of the war, with the lowest loss rate per sortie of any American bomber in the European theater. The R-2800s carried it through mission after mission, reliable, powerful, forgiving of everything except a pilot who did not respect the aircraft's demands. The R-2800 found its true destiny in single-engine fighters, and it found it spectacularly. The Republic P-47 Thunderbolt was the largest, heaviest single-engine fighter of the war. It weighed over 7 tons fully loaded. It was enormous. Pilots who transitioned to the P-47 from lighter fighters described sitting in the cockpit as being inside a living room with a propeller attached. The aircraft was powered by an R-2800 driving a 12-foot propeller through a reduction gear, with a General Electric turbocharger mounted in the rear fuselage that fed compressed air through a long duct to the engine's supercharger. The turbocharger gave the P-47 its high-altitude performance. Above 25,000 feet, the Thunderbolt was as fast as anything in the sky. At lower altitudes, its weight made it less maneuverable than the Messerschmitt Bf-109 or the Focke-Wulf FW-190, but the R-2800's power and the aircraft's robust construction made it a devastating ground attack platform that could absorb punishment that would have destroyed a lighter fighter. The stories of R-2800 durability in the P-47 became legend. Thunderbolts returned to base with cylinders shot away, with chunks of cowling missing, with oil streaming from holes that would have killed a liquid-cooled engine in seconds. The air-cooled radial's tolerance for battle damage was precisely what Rentschler had predicted 20 years earlier. A bullet through a cylinder reduced the engine from 18 cylinders to 17. It lost power, ran rough, vibrated, but it kept running. A bullet through a Merlin's coolant jacket was a death sentence. A bullet through an R-2800 cylinder was a bad day at work. The Grumman F6H Hellcat was the R-2800's other masterpiece. Designed specifically to counter the Mitsubishi Zero, the Hellcat was not the most advanced fighter of the war. It was not the fastest, the most maneuverable, or the elegant. What it was, above all else, was reliable. The R-2800 in the Hellcat started when you pushed the starter button. It ran at the power setting you selected. It did not overheat, did not swallow valves, did not catch fire from its own exhaust. It brought you home. The Hellcat's combat record was devastating. Navy and Marine pilots flying F6F Hellcats were credited with over 5,000 air-to-air kills during the war, more than any other Allied fighter. The aircraft's kill ratio was 19-1. For every Hellcat lost in air combat, 19 Japanese aircraft went down. Much of that success was due to improved pilot training, superior tactics, and the advantages of radar-directed fighter control. But the foundation of all of it was the engine. The R-2800 gave the Hellcat the power to climb, the speed to pursue, and the reliability to be where it needed to be, mission after mission, carrier launch after carrier launch, in the salt air and tropical heat of the Pacific that corroded metal and rotted rubber and tested every mechanical system to the limits of its design. The late-war R-2800 variants introduced water injection, a system that sprayed a water-alcohol mixture into the engine's intake during maximum power settings. The water absorbed heat from the combustion process, allowing higher manifold pressures without detonation. The effect was dramatic, a burst of emergency power, sometimes called war emergency power, that could push the engine's output well beyond its normal rating for short periods. Pilots used it in combat when they needed every last horsepower, in a climb to intercept, in a dive to escape, in the moments when the margin between life and death was measured in knots of airspeed. The wire that broke when you pushed the throttle past the military power stop and into the war emergency range was, for many pilots, the last barrier between normal flying and the desperate physics of survival. The Vought F4U Corsair, with its distinctive inverted gull wing designed to accommodate the massive 13-foot four-blade propeller without requiring impractically long landing gear, was perhaps the most aesthetically striking fighter of the war. It was also one of the most effective, serving with distinction from Guadalcanal to Okinawa and beyond, first with the Marines and then with the Navy once the carrier landing difficulties of the early versions were resolved. The Corsair's R-2800 ran at higher power settings than the Hellcat's version, producing more horsepower, but also generating more heat, more stress, more wear on every bearing and seal and gasket in the engine. The maintenance crews who kept the Corsairs flying on the primitive airstrips of the Pacific Islands performed miracles of improvisation, changing cylinders in tropical downpours, adjusting valve clearances with tools that rusted overnight in the humid air, keeping the R-2800s running in conditions that the engine's designers in Connecticut had never imagined and would not have believed. The R-2800 earned its reputation for reliability not because it never failed, but because when it did fail, the failure was usually gradual rather than catastrophic. This is a distinction that matters more than any specification sheet can convey. The R-3350, which powered the B-29, failed catastrophically. Its magnesium crankcase caught fire at 5,600 degrees. Its wing spar burned through in seconds. Its failures killed entire crews without warning. The R-2800 did not do this. When an R-2800 began to fail, it complained first. Oil pressure dropped slowly. Cylinder head temperature crept upward. The engine ran rough, vibrated, lost power. It gave the pilot time to reduce power, time to turn toward friendly territory, time to look for a place to land or a spot to bail out. The R-2800 did not betray its pilot, it warned him. This was not an accident of design, it was a consequence of the engine's fundamental conservatism. The R-2800 was not the most advanced engine of its era. Its competitors, the R-3350, the Napier Sabre, the Rolls-Royce Griffin, pushed the boundaries of power density and mechanical sophistication in ways that the R-2800 did not attempt. The R-2800 was, by deliberate choice, a conservative design. Its compression ratio was relatively low, which meant it was less thermally efficient than it could have been, but also less likely to suffer detonation damage. Its bearing surfaces were generous, which added weight, but also provided a margin of safety when lubrication was compromised. Its cylinder construction used forged heads rather than the cast heads that plagued some competitors. More expensive to manufacture, but more resistant to cracking under thermal stress. The result was an engine that was not the best at anything, but was the best at everything taken together. It was not the most powerful per cubic inch, it was not the lightest per horsepower. It was not the most fuel efficient, but it was the most reliable, the most forgiving, the most resistant to the 1,000 forms of destruction that combat inflicts on machinery. And reliability, in a war where engines flew until they were shot down or worn out, was the only metric that mattered. By the war's end, Pratt Whitney and its licensees, including Ford Motor Company, which built R-2800s at its factory in Dearborn, Michigan, had produced over 125,000 double Wasp engines. 125,000! It was one of the largest production runs of any single aircraft engine model in history. These engines powered more different types of American combat aircraft than any other engine. They accumulated more combat hours than any other engine, and they brought more pilots home alive than any other engine. The Ford connection is worth pausing on. Henry Ford, the man who had invented the modern assembly line, put his factories and his methods to work building an engine that was originally hand-assembled by craftsmen in East Hartford. Ford's engineers studied the R-2800's blueprints and saw opportunities for mass production that Pratt & Whitney's tradition-bound workforce had not considered. They designed jigs, fixtures, and tooling that allowed less skilled workers to assemble components that had previously required experienced engine builders. They applied statistical quality control methods borrowed from automobile production. The result was an R-2800 that was identical in performance to Pratt & Whitney's own product, built faster and, Ford would argue, though Pratt & Whitney would contest it, with tighter quality tolerances. Pratt & Whitney and its licensees delivered 363,619 engines of all types during the war, 50% of all aircraft engines produced in the United States. Curtiss-Wright contributed 35%. The balance came from smaller manufacturers. Pratt & Whitney did not merely build the best engine, it built half of everything. The company's dominance was so complete that the American Air War, in every theater, on every front, over every ocean, was, in a very real sense, a Pratt & Whitney war. The Germans and the Japanese had nothing that compared. Not because they lacked engineering talent, they had talent in abundance, but because they lacked the industrial depth to mass-produce a reliable 18-cylinder radial at the volumes and quality levels that the Americans achieved. The Germans relied primarily on liquid-cooled inline engines, the Daimler-Benz DB601 and 605, the Junkers Jumo 211 and 213, engines of sophistication and performance that were, in many ways, individually superior to anything the Americans built. The DB605, which powered the late-model Messerschmitt Bf 109, was a precision instrument, a jewel of German engineering, capable of extraordinary specific power output. But it was a jewel that shattered when struck. A single bullet through the coolant system was fatal. A single hour of overheating could warp the cylinder block beyond repair. And the German engine factories, under constant Allied bombing, could not produce them in the quantities needed to replace combat and maintenance losses. Germany did produce radial engines. The BMW 801, which powered the Focke-Wulf FW190, was an excellent design with an innovative automatic engine management system that simplified pilot workload. But the BMW 801 produced roughly 1,600 horsepower at its peak, adequate for 1941, increasingly insufficient by 1944. The R-2800, by contrast, was producing 2,500 horsepower in its late-war variants with water injection. The gap was not merely numerical, it was structural. The R-2800 had room to grow because Pratt & Whitney had built conservatism into the design from the start. The bearing surfaces could handle more stress, the crankshaft could absorb more torque, the cooling system could dissipate more heat. When higher-octane fuel became available, the R-2800 could exploit it without self-destructing. The German engines, already operating near their design limits, could not. The Japanese had their own radial engines, the Mitsubishi Kasei,
the Nakajima Homare, and some of them were competent designs. The Homare, in particular, was an ambitious 18-cylinder radial that attempted to match the R-2800's power output. But it was rushed into production without adequate development time, and it suffered from chronic overheating, poor reliability, and manufacturing quality that varied wildly from factory to factory as Japan's industrial base deteriorated under the combined weight of raw material shortages and American bombing. The Homare-powered aircraft, the Kawanishi N-1K Shiden and the Nakajima K-84 Hayate, were occasionally brilliant in combat, but could never be fielded in reliable numbers. The engine that was supposed to match the R-2800 ended up illustrating, by its failures, exactly why the R-2800 succeeded, not through ambition, but through the unglamorous discipline of doing ordinary things extraordinarily well.
But the war did not care about averages. The war cared about specific moments, specific aircraft, specific engines that failed at the worst possible time in the worst possible place. The R-2800 failed in the cold. At 30,000 feet, the outside air temperature was minus 40 degrees, and the oil in the engine, even the special low-viscosity oils developed for high-altitude operations, thickened and resisted flow. An engine that had been running perfectly at 20,000 feet might begin to starve for oil at 30,000. Its bearings running hot as the oil pump struggled to push thickened lubricant through passages designed for a fluid of different viscosity. The P-47 pilots who escorted bombers at high altitude learned to watch their oil pressure gauges with the same intensity that a hospital patient watches a heart monitor. A slow decline in oil pressure at altitude was a signal to begin descending before the decline became a crisis. The R-2800 failed in the heat. In the Pacific, where ground temperatures exceeded 100 degrees and the humidity turned the air into a steam bath, the engines overheated during taxi. Pilots learned to minimize their time on the ground, to run up as quickly as possible, to take off before the cylinder head temperatures entered the danger zone. A Corsair that sat on a tropical runway with its engine idling for 10 minutes was a Corsair that might not make it to altitude without an overheating incident. The air-cooled engine needed air, and air on the ground, still, hot, saturated with moisture, was not the air the engine had been designed to breathe. The R-2800 failed in the salt. Carrier-based aircraft lived in a corrosive environment that ate metal the way acid eats paper. The salt spray, the humid sea air, the occasional wave that crashed across the flight deck and soaked everything in brine, all of this attacked the engine's aluminum and magnesium components. Corrosion crept into the cooling fins, reducing their effectiveness. It attacked the ignition harness, causing misfires. It infiltrated the carburetor, depositing crystals that disrupted fuel metering. The maintenance crews on carriers fought a continuous battle against the sea itself, washing engines with fresh water after every mission, coating exposed surfaces with preservative compounds, replacing corroded components with a frequency that would have been considered excessive on a land-based aircraft. And the R-2800 failed in combat. Not often, not frequently enough to change the statistics, but often enough that the men who flew behind it knew, in the honest quiet of their own minds, that the engine's reputation for reliability was a tendency, not an absolute. A piece of shrapnel in the right place, through an oil line, through a magneto lead, through the carburetor throat, could kill the engine as dead as if it had been hit by a wrecking ball. The R-2800 could survive damage that would kill other engines, but it could not survive everything. No engine could. After the war, the R-2800 did what great engines do. It grew up. The wartime versions had been designed for power and combat survival, with overhaul intervals measured in hundreds of hours. The civilian versions, developed for the Douglas DC-6, the Martin 404, and the Convair 240, the airliners that connected American cities in the years before the jets, were designed for a different world. A world where engines needed to run not for hundreds of hours, but for thousands. a world where an engine failure was not a combat emergency, but an unacceptable threat to paying passengers who had purchased a ticket with the reasonable expectation that they would arrive alive. Pratt Whitney's engineers, freed from the desperation of wartime development, refined the R-2800 into a civilian masterpiece. They reduced the power output to levels that the engine could sustain indefinitely. Cruise settings that used barely half of the engine's maximum capability, leaving an enormous margin of safety. They improved the lubrication system, adding better filtration and more precise oil metering. They redesigned the accessories, the fuel pumps, the generators, the hydraulic pumps that hung from the engine like mechanical parasites for accessibility and serviceability. A maintenance crew could change a magneto on a DC-6's R-2800 in 30 minutes. On a wartime Corsair, the same job took 2 hours, much of it spent contorting into spaces that the cowling designer had apparently intended for a man without elbows. They developed procedures that were so thorough and so well documented that an R-2800 rebuilt at any overhaul facility in the world would perform identically to one rebuilt at any other. The time between overhauls climbed from the wartime figure of a few hundred hours to over 1,000, then 2,000, and eventually beyond 3,000 hours for the best-maintained civilian engines. Airlines tracked every engine by serial number, logging every hour, every oil change, every cylinder replacement, building a history for each individual engine that allowed them to predict failures before they occurred. The DC-6, powered by 4 R-2800s, became the workhorse of post-war American aviation. It was the first airliner that could fly non-stop coast to coast with a full load of passengers. It was pressurized, comfortable, fast enough to make the transcontinental journey in under 10 hours. The passengers who settled into their seats in order to cocktail as the engines thrummed outside the windows did not think about what was happening inside those cowlings. They did not think about the 18 pistons in each engine, rising and falling 2,700 times per minute, each one generating a force of several tons on each power stroke. They did not think about the crankshaft absorbing those forces and converting them into the smooth rotation that turned the propeller. They did not think about the oil flowing through passages the diameter of a pencil, carrying away heat that would have melted the bearings without it. They thought about their destination. They thought about the magazine in the seat pocket. They thought about dinner. The engine had earned their indifference. That was the highest compliment a machine could receive. The R-2800 in civilian service was, by every measure, a different engine from the R-2800 at war. Not because the hardware had changed fundamentally, but because the way it was used had changed completely. The wartime engine ran at power settings that shortened its life in exchange for speed. The civilian engine ran at settings that extended its life in exchange for economy. The wartime engine was expendable. The civilian engine was an investment. This is the paradox at the center of the R-2800's story. The engine that was designed to be expendable turned out to be the most durable. The engine that was built to be thrown away after a few hundred hours of combat could, when treated with care, last for decades. The conservatism that Pratt Whitney's engineers built into the design, the low compression ratio, the generous bearing surfaces, the forged cylinder heads, was intended to provide a margin of safety in combat. In peacetime, that same margin became a margin of longevity. The engine that was built to survive bullets turned out to be even better at surviving time. The R-2800 remains in service today, nearly 9 decades after the first prototype ran. Rebuilt double Wasps power-restored warbirds at air shows around the world, P-47s and Corsairs and Hellcats and Bearcats, their engines overhauled by specialists who have devoted their careers to keeping these machines alive. Overhauled R-2800s command prices that reflect not just their historical significance, but their continued mechanical viability. An R-2800 that was manufactured in 1944 by Ford Motor Company in Dearborn, Michigan, properly overhauled and maintained, can run today with the same reliability it demonstrated when it was new. The basic design is that good. The metallurgy is that sound.
The engineering is that honest.
125,000 engines, more than any other 18-cylinder radial in history. They powered the fighters that won air superiority over Europe and the Pacific. They powered the bombers that struck the bridges and rail yards and airfields that sustained the German and Japanese war machines. They powered the night fighters, the Northrop P-61 Black Widow, the last great American combat aircraft designed around the R-2800 that intercepted the bombers threatening the fleet. They powered the cargo planes that carried the supplies that fed the armies that liberated the continents. And some of them failed. Return to that B-26 over France, summer of 1943. The pilot whose name was lost, the oil line severed by shrapnel no larger than a man's fingernail, the engine that seized, the propeller that stopped, the yaw that pulled the aircraft into the trees. The R-2800 in that aircraft was a perfect engine. It had been assembled to specification. It had passed every test. It had been maintained by competent mechanics. It had run flawlessly for every mission prior. And it died because a piece of German steel happened to strike the one component that could not survive being struck, the artery that carried the blood the engine needed to live. Some of them threw connecting rods through their crankcases at 20,000 feet, the metal fatigued by vibrations that no engineer could entirely predict. Some of them overheated on tropical runways and never made it off the ground, their cooling fins clogged with the red volcanic dust of a Pacific island that the engine's designers in Connecticut had never heard of. Some of them simply wore out, their bearings ground down by sand or salt, or the relentless friction of metal against metal over hundreds of hours of combat, their cylinders scored by abrasive particles that no filter could entirely exclude from the combustion air of a war zone. The pilots who survived those failures, who glided to crash landings in farmers' fields, who bailed out over the English Channel into water so cold it stopped the heart in minutes, who dead-sticked onto carrier decks with frozen propellers and locked brakes, did not curse the R-2800. They did not blame it. They knew that the engine had given them everything it had, and that everything was not always enough. They knew that the difference between coming home and not coming home was sometimes a quarter-inch piece of German steel that happened to hit an oil line instead of a cylinder fin. They knew that reliability was a word that belonged to statistics, not to individuals. A 99% reliable engine still kills one crew in 100, and if you are that one, the 99% means nothing at all. The Pratt Whitney R-2800 Double Wasp was probably the most important piston aircraft engine ever produced. That is not my assessment. It is the assessment of aviation historians who have spent their careers studying the engines that powered the aircraft that fought the most destructive war in human history. It powered more types of American combat aircraft than any other engine. It produced more horsepower per cubic inch than any previous air-cooled radial. It achieved a ratio of 1 horsepower per cubic inch, a benchmark that was considered nearly impossible for an air-cooled engine and that was not surpassed until the jet age made the question irrelevant. But it was still a machine, and a machine in war is not a machine in a laboratory. It is a machine in a world of shrapnel and sand and salt and cold and heat and vibration and the accumulated indifference of a universe that does not care whether the oil pressure holds for 1 more hour or 1 more minute. America trusted the R-2800 to survive, and it did survive 125,000 times across every ocean and every continent where the war was fought. It survived because it was brilliantly designed, conservatively engineered, and meticulously manufactured by a company that believed, with the fervor of a religious conviction, that air-cooled engines were the future of aviation. But it did not survive every time. It could not. No machine can. And the men who did not survive, the pilot over France, the Corsair pilot in the Pacific, the Hellcat pilot whose engine quit on a carrier approach in the dark, they are the footnotes in the legend, the statistical remainder. the fraction of 1% that the overall reliability rate does not account for. They trusted the engine. The engine was worthy of trust, and still, for some of them, trust was not enough. That is the truth about the R-2800. Not that it was perfect, not that it was invincible, but that it was as close to both as any machine built by human hands has ever come, and that the distance between close and actual in a war is measured in graves.